Similar to the effect that motion has on time, there's a relativistic effect involving length as well. Any moving object is shortened along the direction of motion. This effect is known as length contraction. Length contraction is the second necessary consequence of Einstein's postulate that the speed of light is the same for all observers. We now know beyond all doubt that both length contraction and time dilation actually occur. With time dilation and length contraction together, we can now see the final solution of how Einstein's postulate allows the two starships to measure the same speed of light. As the upper starship passes, we see that the starship's clock runs slower than the one at rest. We also note that the starship itself is shortened or contracted. After 12 seconds elapse on the stationary clock, we see that only 9 seconds elapse on the moving clock, not the 6 seconds we assumed in an earlier example. But due to length contraction, the moving ship and all the rulers aboard are contracted just enough to make the measurement work. According to the crew, the beam of light travels 9 light seconds and 9 seconds. They now report that the light beam travels at the correct speed of 1 light second per second.
Does that really happen?
Sure does. Thousands of experiments have been done since Einstein stated his postulate, and every one has shown time dilation and length contraction are real and really happen.
Back in 1971, 4 cesium atomic clocks were synchronized and flown on commercial planes that circled the Earth twice, and then compared to the reference clock at the U.S. Naval Observatory. Sure enough, the moving clocks differed from the reference clock by exactly the amount predicted by relativity. Let's look at it a little differently. Here's a graph of a car traveling due east at its maximum speed of 100 miles per hour. It is making no progress in the northward direction. All of its speed is going east. Now let's turn a little to the northeast. Even though the car is still doing 100 miles per hour, it is going less than 100 miles per hour in the east direction, because some of the speed is being used to go north as well. Space and time can be thought of in the same way. Everything in the universe is traveling through space and time at the speed of light, the maximum speed available. Picture time replacing east and space replacing north in the car example. If you are sitting still in space, not going north, you are traveling at the maximum speed through time, east. But if you start moving in space, north, your progress through time will slow down, since some of your speed has been diverted. The faster you go through space, the slower your progress through time. If you could travel at the speed of light in the space direction, you would make no progress in the time direction at all. Time would stand still, as it does for a beam of light. And if you could go faster than the speed of light, you could travel backwards in time. Remember, if different observers must always agree on the speed of light, then they must disagree on the components of speed. Time and distance. Time and distance both shorten for moving observers. These unusual effects of relativity, time dilation and length contraction, depend dramatically on your velocity. At everyday speeds, they are simply not noticeable. The fastest that humans have ever traveled is a few miles per second. a tiny, tiny fraction of the speed of which light travels, 186,000 miles per second. But in Einstein's universe, space and time are no longer absolute. There is no single time that exists for everyone in the universe, no distance in space that everyone can agree on. Space and time, like classical velocities, are only relative. Einstein preferred to think of a single entity, space-time, in which events and measurements took place. One observer might see two events as separated by a large distance, but occurring at almost the same point in time, while another observer views the same two events as occurring nearby in space, but far apart in time. While the individual space and time separations will be different, Einstein's equations allow the two observers to agree on the combined distance through space-time. It wasn't just her idea about space and time that were altered by Einstein's theory of relativity. Einstein also realized that we should have to reconsider the whole idea of energy. If we look closely at a proton in a particle accelerator, it is easy for scientists to see that only some of the energy that we apply actually increases the speed of the particle. The remainder simply increases the mass of the particle. The faster it goes, the heavier it gets. When it is traveling at almost the speed of light, almost all of the energy we apply just makes it heavier. That is why a particle with mass can never reach the speed of light. It gets heavier instead of going faster. This fact is summed up in Einstein's most famous equation, perhaps the most famous equation in all of science. E equals mc squared. Besides defining the energy of a body at rest, the equal sign also indicates that matter can be converted into energy, and vice versa. The conversion factor, the speed of light squared, is an enormous number. According to Einstein's equation, a tiny bit of mass can be converted into an enormous amount of energy. But there is more to E equals mc squared than atomic bombs. The recognition that mass can be converted into energy made it possible to understand the source of energy of the sun and the stars, still a mystery in Einstein's day. It also paved the way for the exploration of the mysterious realm within the atom, and the discovery of a whole menagerie of new particles, created from pure energy in powerful particle accelerators. In the early 21st century, nuclear power plants provide about 20% of our nation's electricity, converting a tiny fraction of mass of each uranium atom into usable energy. Perhaps even more than his idea about space and time, Einstein's mass-energy equation has had a far-reaching impact on our world and our way of life.